Name the biggest number you can. Go on, pick one. Whatever you picked, I can beat it. I just add 1. And then you can beat me, and round we go forever. So there's no biggest number. Done, right? Except that's the boring answer to the wrong question. Because hiding inside that first question is a second one, and that one does have an answer, a real specific biggest number. So let's go find where it lives.
Is there a biggest number? Sounds like one question. It's actually two. The first is mathematical. Does a largest number exist? No. For any number n, you can always write n plus 1. Arithmetic never runs out. But the second question is stranger. Could a number actually be written down, stored somewhere physical? Because writing takes matter. Chalk marks, computer memory, particles arranged into states. And the observable universe appears to contain only a finite amount of stuff. So if every written number needs a physical representation, then only finitely many complete representations can exist. So the limit is not on numbers themselves. Mathematics stays unbounded. The limit is on representation, not the largest number, just the largest one reality can physically hold.
All right, let's actually count. We start with every particle in the observable universe, every speck of matter, everywhere we can see. Physicists put that number at around 10 to the 80. That's a 1 with 80 zeros after it. Written out longhand, it spills off this board, then the next one, and keeps going. So already we're dealing with quantities far beyond ordinary intuition. But here's the important shift. Particles are the wrong thing to count. The deeper limit isn't how much stuff exists. It's how many different ways that stuff could be arranged. Take the same particles and move them around. Change the field slightly. Flip quantum states. Each distinct configuration counts as a different possible state of reality. That's what physicists mean by information. And information is physical. You cannot store unlimited distinctions inside a finite region of space. If you try to pack in too much structure, too much energy density, gravity takes over. The region collapses into a black hole. That turns out to matter enormously, because black holes appear to be the densest information storage objects physics allows. And strangely, their information capacity scales with surface area, not volume. That idea leads to something called the holographic bound. The result is an estimated ceiling for the observable universe, around 10 to the 123 bits. Not particles, bits. About 10 to the 123 distinguishable states the observable universe can physically encode. Every arrangement of every particle, every field, every possible configuration, all of it fits beneath that line. Finite. So this number is different from an ordinary large number. It's a physical limit, a storage budget imposed by reality itself. There genuinely appears to be a maximum amount of information the observable universe can hold. Now keep that ceiling in mind, because mathematics contains numbers so much larger that this entire bound starts to look small. Mathematics often builds new operations by repeating old ones. Addition becomes multiplication. Multiplication becomes powers. And then the same pattern continues upward. Now write 3 up arrow 3. One arrow just means powers. So 3 up arrow 3 is the same as 3 to the third power. 3 times 3 times 3, 27. Then comes the first real jump. 2 arrows means you stop multiplying and start stacking powers into a tower. Write it vertically. 3 to the 3 to the 3. The powers stack upward. So 3 double arrow 3 means 3 raised to the power of 3 raised to the power of 3. Not parentheses, a tower. And even that small tower already becomes enormous. 3 double arrow 3 equals 3 to the 27th power, which is about 7.5 trillion. Now 3 arrows. This is the part that quietly breaks intuition. 3 triple arrow 3 does not mean a slightly taller tower. It means the height of the tower becomes the previous number. Write it slowly. 3 triple arrow 3 equals 3 double arrow, open parentheses, 3 double arrow 3, close parentheses. The tower height is no longer 3. It's 7.5 trillion high. Not 3 high, 7.5 trillion high. So how large is that? Take the smallest meaningful length in physics, the Planck length.
Across the observable universe, end to end, you can fit about 10 to the 62 of them. Fill the entire universe with Planck-sized cubes, roughly 10 to the 185. Now count every cube once per nanosecond since the Big Bang. You reach about 10 to the 212. That already strains comprehension, and it is nowhere near large enough. Even the early levels of that tower rush past numbers like 10 to the 212 almost immediately, then continue upward for 7.5 trillion more layers. Each new arrow is not merely larger, it changes the kind of growth itself. Now we can see what Ronald Graham did with it. He was studying a real problem in combinatorics. Roughly speaking, coloring connections inside higher dimensional cubes and asking when certain patterns become unavoidable. He needed an upper bound. This was the number he used. We begin here. 3 with 4 arrows, 3. Written on the board, 3, up, 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 3. Call that layer 1. And remember, 4 arrows is already beyond physical representation, so layer 1 is already unimaginably large. Now layer 2 uses the same form again, 3 arrow 3. But the number of arrows is no longer 4. The number of arrows is layer 1 itself. A number too large to write becomes an instruction count. Then layer 3 uses layer 2 as its arrow count, and upward it goes. Each layer determines how many arrows appear in the next one. Not 6 layers, not 10. 64 layers. At the top sits Graham's number. Finite, precisely defined. We even know it ends in a 7. But if every particle in the observable universe were used to write its digits, space would run out long before the number did. For years, this was the largest number ever used in a serious mathematical proof. But here's the number that dethrones it. And this one comes from, of all things, a game. On the chalkboard, the trees are tiny, just dots joined by lines. Each dot gets a label, 1, 2, or 3. The rule is simple. No earlier tree is allowed to hide inside a later one. With one label, every tree eventually looks the same, so tree of 1 is 1. With 2 labels, you can dodge repetition a little longer, but only a little. Tree of 2 is 3. So naturally, 3 labels should give a few more possibilities, maybe 10, maybe a 100. Instead, the number detonates into something called tree of 3. And tree of 3 doesn't merely exceed Graham's number. It makes Graham's number effectively vanish by comparison. The difference is beyond scale. All from a finite game about avoiding repeated patterns. And there is still no largest number. There never will be. So, is there a biggest number? In mathematics, no. Take any number, add 1, and you have a larger one. That part is simple. But now change the question. Can reality actually hold a largest number? A number written down, stored, physically represented somewhere in the observable universe? There, physics says yes. The universe appears to contain only a finite amount of information, so there is a ceiling on the largest number reality could ever fully store. And then comes the strange part. Beyond that fence sit Graham's number and tree of 3, both finite, both precisely defined, yet so large that the observable universe could never write out their digits. Because mathematics compresses ideas. A few chalk symbols can describe structures far larger than physical reality can contain. So the fence belongs to physics, not mathematics, which leaves a different question entirely. What is the biggest number anyone has ever named? It only gets bigger and stranger from here. Subscribe and like so you don't miss what's coming.